He's professor at the Department of Computer and Information Science and Engineering at the University of Florida. Before this, he received his PhD at the University of Southern California and was at Yale as a postdoc, associate research scientist, and assistant professor. His research interests are image analysis, machine learning, and computational mathematics. And yeah, I would hand over to you for your presentation now.
Oh, thank you so much. Can you hear me?
Yes, that's working.
Okay, wonderful. Thanks. I want to thank the organizers, especially Tolga, for setting this up. It's an absolute privilege to talk to you about shape analysis and quantum approaches in shape analysis. Let me just quickly go over the roadmap. One point of departure in this talk relative to the previous talks by Michael and Roberto is that this talk's primary focus is on quantum approaches in shape analysis and not specifically quantum computing. Though, of course, the hope is that these quantum approaches will pay off in the form of, let's say, Hamiltonians for annealing or even other tensor decompositions in quantum computing. The talk is structured to take you through shape analysis, specifically from distance functions, distance transforms, from unsigned distance transforms, which are a shape representation. And specifically what we'll do is we'll start with Hamilton-Jacobi theory for distance functions and then move to the equivalent Schrodinger representation. Thereby, people can see the mapping as you go from a classical approach to a quantum approach. Then we will go from unsigned distance functions to signed distance functions, and specifically wave representations of signed distance functions, bringing in the complementarity angle to the shape representation. This will be followed with a full-blown complex wave representation showing off what entanglement can do for you, leading to shape matching. And this will be a nice follow-up, I think, in some ways to what Michael presented. And if there's time, we'll round out with representational issues and thoughts for the future. Okay, now I don't think we can expect too much familiarity with shape analysis. So what I'll do is I'll begin with distance transforms and set them up in the simplest way possible. And having done that, then walk you through going from a Hamilton-Jacobi representation to a Schrodinger representation. So distance transforms have been around in computer vision for probably 40 years, 40 or 50 years. And if you go back to the early 90s, the set of data structures like level sets and fast marching methods, etc., became very standard methods for fast computation of distance transforms, and also further with things like the iconal equation, etc., which we'll briefly allude to in this talk. Okay, now the interesting thing is that the connection between distance transforms and Hamilton-Jacobi theory, that is classical physics, is well established. You will see countless numbers of papers in the literature that discuss this connection and then leverage it as well. But you won't find as much that take you from Hamilton-Jacobi theory to the equivalent Schrodinger representation. And that's where we come in to fill in the gap. Okay, so let's start. So if you have no background at all in distance functions and no background in Hamilton-Jacobi theory, don't worry about it. This will be, in a sense, a tutorial for it. So imagine you have a set of points in R2, and it's just a Euclidean space. What you want to do in an unsigned distance function or an unsigned Euclidean distance transform is for each point on the grid, you want to find the distance to the nearest point of the set of points that you have, which are the set of points yk. So at each point on the grid, you're going to find the distance and you're going to mark it with the distance to the nearest point. Now, this goes by many different names. You may have encountered this in 2D and 3D as the Voronoi problem, but we won't go into too many computer science data structures here. We'll just stay with distance transforms and the connection to Hamilton-Jacobi. So when you do this, when you set up S of x, where x is the set of points on the grid, you get an unsigned distance function. What I mean by unsigned is that there's no notion of an inside of a shape versus the outside of a shape. What you get is just a geometric object, which is called the distance function. And later on, we will introduce signed distance functions where you will have an inside and an outside, and that will be the point of departure from these unsigned distance functions. Okay, so you compute then the distance from yk for every point on the grid, and you find the minimum distance. And what you notice right away is that this distance function has the property that almost everywhere its gradient magnitude is 1. And the reason for this is that you can think of this as a problem where you have wavefronts emerging from each of those points, and they move until they meet wavefronts coming from other points. And effectively what happens is the distances that are stamped out basically have a gradient magnitude of 1, and they look like cones, as I'll show you in a minute. The fast marching and the fast sweeping methods, they took advantage of this and came up with efficient solutions, which are order n log n, or even order n in some circumstances. And the important thing here is that analytical solutions, while being unavailable, you have very good data structures that are capable of solving this problem. So the Hamilton-Jacobi equation for this is the magnitude of grad s is equal to 1. That is sx squared plus sy squared, where sx, sy are the gradient, equals 1 almost everywhere. At the points themselves, s takes the value 0, and that's called the 0 level set, which will be important later on. And basically what happens is that you want to find this function s at every point on a grid. Okay, so this is how you go to the Hamilton-Jacobi theory, where you have the scalar field s of x that you're trying to compute at every point. Now, this is what the distance transform looks like for a random set of points in R2. It's basically, as you can see, a set of cones with values of 0 at the points themselves, and then the distance increases as you move away from it. Now, what you can do is you can leverage the fact that Hamilton-Jacobi theory and Schrodinger equations are very tightly connected. And what you can actually do is you can try and write down a static Schrodinger equation for this problem. So I want you to not bother about this particular standard Schrodinger equation, but instead focus on the static Schrodinger equation that I've written down here, which will look mysterious at this point in time, but that's okay. We'll set it up and show you the connection between the static Schrodinger equation that I've written down here and the Hamilton-Jacobi problem that we set up for the distance function. So specifically, consider a static Schrodinger equation, which is minus h cross squared del squared psi plus psi equal to psi naught. And psi naught is a set of initial conditions. You can think of psi naught as an initial wave taking the value something like 1 at all the points themselves. And you're going to then try to find a solution psi at every other point in space. This also goes by the name the Screen-Poisson equation. And for the purposes of this discussion, think of h cross now as just a computational free parameter, which can take values very close to 0. Okay, so what we've done is we've mysteriously introduced a static Schrodinger equation, and the payoff is going to be that we will connect this Schrodinger equation back to the Hamilton-Jacobi equation that we started things off a couple of slides ago. So what is the relationship? The relationship basically is this, that if you start with grad s equals 1, and you write down minus h cross squared del squared psi plus psi equal to psi naught, then if you set up psi of x equal to e to the minus s over h cross, where s, I'm deliberately abusing notation and using the same s that I have here as that of the Hamilton-Jacobi equation, then basically what happens is that if you write down the actual differential equation by substituting e to the minus s over h cross, instead of psi, you end up getting the magnitude squared of the gradient, grad s squared minus h cross squared del squared s equals 1, which tends to grad s equals 1 as h cross tends to 0. So basically, I want the takeaway from this is that the nonlinear Hamilton-Jacobi equation is classical. It's basically magnitude of grad s equal to 1, except where s goes to 0 at the level set, where the points are. The linear Schrodinger equation, if you make the connection that psi of x equals e to the minus s over h cross, then you end up getting something very similar, which is the magnitude of grad s squared minus h cross squared del squared s equal to 1. And for those people in the know, this is called a viscosity equation for the Hamilton-Jacobi equation, but we don't need to worry about that at this point. Another takeaway here is that note that the wave function is real. This will be quite important as we proceed later on, because later on what will happen is we will make the wave function complex in order to be able to go from the unsigned distance function to the signed distance function. But for now, all I want you to take away from this is that classical methods solve grad s equals 1. What we can do, if we so desire, is that we can solve the linear Schrodinger equation. The classical equation does not have a closed form solution for s, but what we can do is we can take minus h cross squared del squared psi plus psi equal to psi naught and attempt to solve it in terms of a closed form solution, and then find out how long it takes to compute it. Okay, so this, I want to give a shout out to Jeremy Butterfield, a wonderful paper that was written many years ago called On Hamilton-Jacobi Theory as a Classical Root of Quantum Theory, where he basically pointed this out, that you can think of quantum theory having a classical root in Hamilton-Jacobi theory, and that pretty much then set up everything that we did, which is to go from static Hamilton-Jacobi equations to the corresponding static Schrodinger equation. Okay, so we can now try to solve this equation, minus h cross squared del squared psi plus psi equals psi naught. Psi naught will be peaked on the actual shape, which are the shape points as we're calling them. It will go down to 0 elsewhere. And there's an analytical solution in 2D. And the solution you get is that you get psi equals k naught, which I'll tell you what that is in a moment, x minus yk L2 norm over h cross. So basically, you have an analytical solution in 2D for the static Schrodinger equation. And this we're calling the Schrodinger distance transform when you take minus h cross log of it, because then as h cross tends to 0, you can relate this distance transform to the original distance transform, which did not have an h cross in it. So essentially what we have done is that we have taken the Hamilton-Jacobi equation corresponding to the unsigned distance function. We've gone to the static Schrodinger equation. We've set up the static Schrodinger equation, and for those people in the know, this is essentially a screened Poisson equation with a forcing function. It has an analytic solution, and the analytic solution is basically has these special functions called k naught, which is nothing but a modified Bessel function of the second kind. And if you look at it carefully, you'll notice that psi of x is just the sum over k naught of x minus y over h cross. You can actually compute this fairly efficiently, because what you can do is you can set up the k naught, which is the Green's function for the problem, put yk as 1 at all the points where actual points are present, and then you can set up this psi of x as a fast convolution using a Fourier transform. So you can set up in 2D and in 3D. There's a corresponding analytical solution in 3D as well. You can essentially set up a fast convolution-based method to solve this, and that's the quantum analog to solving it using fast marching or fast sweeping, as in the static Hamilton-Jacobi equation. Okay, so what does this mean? This means that you can compare these two carefully, right? You have a nonlinear Hamilton-Jacobi equation, a linear Schrodinger equation. The nonlinear Hamilton-Jacobi equation looks like this. The Schrodinger equation is a screened Poisson equation. You have the equivalence between s and psi, and you have no smoothness control because there's no h cross parameter in Hamilton-Jacobi. Here, you're going to have an inherent smoothness due to H cross. The wave function is going to be real. It's not going to be complex. And that's going to correspond to the unsigned distance function. And you can compute this efficiently in order n log n, n being the number of grid points, using a fast Fourier transform. There are no numerical issues for the nonlinear Hamilton-Jacobi equation, but if you were to do this in a classical computer, you're going to have numerical issues due to the negative logarithm, and you may have to go to multi-precision or variable precision numerics in order to be able to carry this out with good precision on a classical computer. Okay, so what we thought was this had good pedagogical value as well, because people can now see the equivalent of a classical method and a quantum method on essentially the same problem. And here, of course, we are thinking of the wave functions as real, and we have the H cross as a computational parameter, which can be sent close to 0. Okay, I will skip over this, except to point out that you can start from a variational problem and end up with a Schrodinger variational problem, and go through the entire sequence from the Lagrangian to the Hamiltonian to Hamilton-Jacobi to Schrodinger. Okay, so you can also take this further, as we did. You can try to approximate the iconal equation, where instead of grad s equals 1, you have grad s equals f of x, which is the iconal problem. You can now set up the corresponding linear Schrodinger equation for this problem as well, and again use the relationship that phi of x is real. I'm using phi here instead of psi, but it's essentially the same thing. And you can think of this s as an approximate distance function, except for the iconal equation. And you can discretize and solve a sparse linear system. The caveat here is that you no longer have a closed form solution for the linear Schrodinger equation, as you did for the distance function, but you can solve it as a sparse linear system, with, of course, the problem being that you may have to use variable precision numerics, because of the fact that if H cross is very small, the linear system is going to be somewhat unstable. Okay, and we carried out some of this for meshes and for retinograms and things like that, just as a showcase that you can do this kind of work. We also made a foray into shapesum shading, but I'm not going to get into that at the moment. Okay, so I want to give a shout out right now to, I checked this with Stephen Jordan who was at NIST and now at Microsoft, who is a quantum computing guru, as to the viability of this kind of a scheme. And the reason why I'm bringing Stephen Jordan up here is that he had the exact same idea, and except that he was going to set this up with Gaussians rather than with the screen Poisson equation as we were doing. And he pointed out to me that to set this up on a quantum computer, the real problem is actually setting up the initial state. Everything else, the fast convolution, the quantum FFT, all of that is doable, but it's actually setting up the initial state that becomes problematic. And I leave that up to future people to try and crack if they're interested in being able to now take this further to a quantum computer as well. Another shout out to Sibyl Tari, who pointed out that all that we had done effectively was go from a nonlinear Hamilton-Jacobi equation to a linear differential equation, and that there was a literature that converted nonlinear Hamilton-Jacobi equations to linear differential equations, and that she had cataloged almost all of these methods, and therefore the Schrodinger equation being linear fits into one of the class of these kinds of linear differential equations. Okay, so let's now move on. Basically, right, what we have done so far is that we've kept things very simple. We started with a set of points in 2D. We set up the unsigned distance function problem. And then from the unsigned distance function problem, we went to Hamilton-Jacobi to Schrodinger, but the wave function was real. So now the question is, can we, instead of having the unsigned distance function problem, can we go to the signed distance function, where you'll have a notion of the inside of a shape versus the outside of a shape? Because the signed distance function will be in 2D. Think of a set of closed curves in the plane, and imagine that you're going to compute the distance function, which is going to take positive values and negative values, depending on whether you're inside the shape or outside the shape. This would mean that we are in the general framework of density estimation, because we're going to basically our wave function is going to be something like the square root of a density function. It's going to be complex. The magnitude of the wave function will be related to the density function on the shape, while the phase of the wave function will be related to the Hamilton-Jacobi field. Okay, so let's set this up. In density estimation, Parson windows are the most popular. And in Parson windows, basically what you do is, if you're given a set of points, you put a Gaussian at each point and you sum up all the Gaussians. But we can do better. What we're going to do now is instead of the Parson window density estimator, which you're seeing right here, essentially what it does is it takes the set of shape points and it puts a Gaussian on each point. And there's an unknown parameter sigma, which is then estimated using maximum likelihood cross-validation. And this is how you estimate a density function for a shape, by putting a kernel function centered at each sample. Why am I mentioning this? The reason for mentioning this is, instead of doing a Parson window where you notice that the density function is coming from a real Gaussian being placed on all the shape samples, what we are instead going to do is we're going to take the complex exponential of the distance function. So imagine you have a distance function. Let it be signed or unsigned, it doesn't matter, but signed would be better because then you'd have the notion of the inside and the outside of a shape. And now consider taking the complex exponential of the distance function. Now, for those of you coming from, and by the way, tau, I'm using tau here because tau is going to be a free parameter, which is going to be akin to h cross. For those of you coming from a physics background, you are going to expect that if I take the complex exponential of a Hamilton-Jacobi field, e to the I s over tau, the magnitude squared of this distance function, and then also the Fourier transform of this complex exponentiated distance function are going to be related to a density. And so that's what we're going to try and show you. Basically, what we're going to show you is that if you take the complex exponential of the distance function and you hit it with the Fourier transform, e to the minus I nu transpose x. So imagine that f of x is in 2D, and nu, therefore, is a vector of spatial frequencies with a frequency along the x direction and a frequency along the y direction. So it's a 2D Fourier transform. Now, imagine that you take the complex exponential, we're going to start calling this the complex wave representation, and you're going to hit it with a 2D Fourier transform and take the magnitude squared of this wave function which has had a Fourier transform operated on it, and you'll normalize it using a constant c to make it integrate to 1. So this is going to be a density function. Now, what we want to show you is that this does something very interesting, sort of bringing out the complementarity that's inherent in taking the complex exponential of a distance function. What is going to happen is that because s of x is a distance transform, and you are taking the complex wave representation and hitting it with a Fourier transform, for values of tau that are very, very small, you're going to have high fluctuations, and most of the fluctuations will cancel out. And in a highly oscillatory integral, what will happen is that only the frequencies at which you get a hit will get picked up. And that's essentially what happens in something called the stationary phase approximation. So what is that? So focus on this integral. You have e to the I s of x over tau. I'm going to now modify the Fourier transform to have s of x minus u transpose x, where u over tau is going to be my frequency. What is going to happen is, with tau, when tau goes very close to 0, this is going to fluctuate extremely with very high oscillations. Most of those oscillations are going to be destructive. But what is going to happen is, at the places where the phase is stationary, you end up getting a stationary phase approximation, where effectively what happens is the stationary phase picks out the places where the gradient of this function, the gradient of s, hits particular frequencies. So effectively what you get is, the takeaway from this is, you get grad s equal to h mu, where basically grad s ends up being picked out at various histogram bins. And you effectively end up in the frequency domain. You can think of the frequency bins as histogram bins. And that when you take the magnitude squared, you end up with something like the density function of the distance transform gradient density function. So how does this work? You take this to be the actual stationary phase approximation, where you're taking the Fourier transform and you're approximating this by expecting tau to be very, very, very small. You get arbitrary phase factors corresponding to the fact that you've not taken the magnitude squared. When you take the magnitude squared and you integrate it, you end up getting that at places where you have spatial frequencies which are picked out by the gradient of the function, you get grad s equals tau nu, and the stationary phase, you get hits at these frequencies. I want to point out that most people coming from a physics background, intuitively, they understand this. They understand that these oscillatory integrals, especially when you hit them with the Fourier transform, that you'll end up picking out the gradient of the Hamilton-Jacobi field. But I want to caution you that when you talk to applied math people, they tend to look at you as if you are from Mars, because they simply don't have this kind of a background, okay? I also want to caution you that the magnitude squared of the wave function doesn't actually give you the correct density function. You do have to integrate it over a small neighborhood in order to make sure that as tau tends to 0, that you get a matching between the density function that you get by taking the Fourier transform of the complex wave representation and taking its magnitude squared. If you integrate it a little bit in the frequency domain, then you can show that you actually get the density function. And we did this calculation laboriously and carried it out analytically and showed this to be valid. Okay, so what does this look like? So essentially, if you look at this distance function of a horse, where we have the color coding is the inside versus the outside, where the zoomed portion is actually showing you the gradients, which are all magnitude 1, but they're going to have different directions depending on whether they are inside or outside. And effectively what happens is we take the e to the I s over tau, and now look what happens when you take the Fourier transform. You'll notice that the Fourier transform, because of stationary phase, is mostly on the hits are on a circle. And the reason for that is, with the gradient magnitude being 1, that shows up in the fact that the Fourier transform of psi of x, the hits that you get as you send tau to 0, occur only effectively on a circle in 2 dimensions and on a sphere in 3 dimensions. So this is the effect of the stationary phase approximation that we just went through. So basically then, you can then carry out the actual histogram of the oriented gradients. You notice now that because the gradients have magnitude 1, you don't need to worry about the magnitude of the gradient in terms of its density function. All of its gradients are mostly magnitude 1, but the direction is important. So effectively, you're doing a density function on the direction of the gradient. And that's why the Fourier transform is only valid at places where you have a circle of frequencies. And if you look at the actual histogram versus the gradient magnitude squared of the magnitude squared of the wave function, you'll notice a pretty good correspondence between the histogram of the oriented gradients computed directly from the gradient, whereas here the gradient is never computed because of complementarity. You're just taking the complex wave representation, taking its Fourier transform, taking the magnitude squared, normalizing it, and then displaying it. So this is sort of an illustration of the complex wave representation and the complementarity principle in action. Okay, so what this means is that you can now start thinking about this complex wave representation as a density function. So you can go from a distance transform now to a density function which is complex, and you can now think of computing things like averages, which you could not do with distance transforms. Distance transforms are not things that you can add, etc. Whereas wave functions being linear, you can add them and you can compute means and things like that. So what we did is we took some brain MRI in 3D and did some computations where we computed averages and then went backward and computed the distance transform of the mean and went back and found an average shape, etc. So you can sort of walk through this kind of a procedure. Okay, so we call this a shape complex atlas, and effectively all it is that you're coming up with a complex wave representation and then coming up with ways by which you can do statistics on it. Okay, so basically, so far, what we've done is we've shown you the advantages of the unsigned distance function. and that of the sign distance function, where we have taken the complex wave representation by taking its e to the I s over tau. But now the question is, can we do more? And so that we'll move towards that right now and bring in the concept of entanglement. Okay, so now consider something that is different from what we've seen so far. Imagine that in addition to the set of points that you have in 2D or in 3D, imagine you also have the orientation. Like imagine that you have the normal to the point of the curve at a set of finite set of points. Or in 3D, imagine that you have a set of points that form a surface, and in addition to the set of points themselves, you have a outward pointing normal corresponding to mu, which is the outward pointing normal at those points. We call this an oriented point set. So in an oriented point set, not only do you have shape locations, but you also have the normals to the shape, and you can think of these normals as either unit vectors or as non-unit vectors. You can work with both representations. And now consider a wave function, which is directly written, not as a Parsons window estimator where you just have a Gaussian, but imagine you've written out a complex representation where you have a Gaussian on the points, but you also have a phase factor corresponding to the normal at those points. So what is going to happen is, if you have points that are nearby and their normals are pointing in a very similar direction, and you're taking the sum of these waves, if you take the magnitude squared of this, these waves that are emanating from along the directions that are in the same direction will have constructive interference, whereas the waves that are coming out of the shape but pointing in different directions will have destructive interference. So essentially what happens is you have a complex wave representation that takes into account the entanglement, where nearby points can affect each other, where as opposed to thinking of these points as just isolated points, you're now, because of the fact that you have this additional information, namely the orientation information, you can think of this as a complex representation with entanglement, where the different waves are entangled with each other. You can, of course, normalize this wave function so that its norm is 1. And the important thing here to take away is in 2D and in 3D, we are giving you curve and surface information, orientation information in the form of nu k is being assumed. Now, the setup that we're going to have, which is slightly different from what I think Michael talked about, is that you can think of this as a template. So you can imagine a situation where you have a template, and a template would have this orientation information, whereas you have a target in a deformable template situation where the targets would be just points, where they wouldn't necessarily have any orientation information. And then the question would be, can you deform this wave function representation onto a target while endowing the target with a set of normals so that it too will have implicit surfaces corresponding to a set of normals that you're going to induce onto the target. So, but the bottom line here, right? The important part is, let's go back now in case I've lost most of you, just notice the important aspect of this wave function. As opposed to the Parsons window density estimator, which is real, we have a complex component, and the complex component has just this orientation information, and therefore this wave function will have a phase, and you can compute the phase of this wave function, which was missing in the original unsigned distance function computation. So we can show you what the difference is from adding this phase information. So the important thing here is you get a completion field in the phase. You can now think of assigned distance function level sets corresponding to these phase contours, and you can also compute inner products of this wave function and end up with kernels, which are going to be related to things like wave kernel signatures in the literature from Daniel Kremer's group, etc. You can get inner products and distances in closed form, but they'll all have this extra information in the form of this orientation information. You can, of course, do PCA and other types of statistics. And in the future, we are actually thinking of you doing P2V mappings. In case you're not familiar with P2V mappings, these are very popular in distance in deep learning right now, where you go from a point set representation to a volumetric representation. And you can imagine that this wave function representation is a very useful volumetric representation, because in addition to being the real numbers being related to the density function, the complex numbers are going to be related to the phase, which will carry level set information. So let's show you what this means. So take a look at the unsigned distance function, and I'm going to show you the level sets of the unsigned distance function. Take a look at this red line, and you'll notice that as you follow the red line, you'll notice that there's no notion of interior and exterior. There's no sense of inside and outside. If there is a shape boundary here, it's missing because there's no notion of inside and outside. In contrast, take a look at the signed distance function coming from the phase. I'm plotting the phase of the wave function, the level sets of the phase. Notice that the 0 level sets of the phase carry the shape information in the form of these level sets, and there can be a notion of an inside and an outside. Okay. In addition to this, the magnitude of the wave function, you can expect it to be highly peaked at these boundaries. So effectively, you end up getting a complex field where the magnitude squared is related to the density function, and the phase of the wave function is related to the signed distance function. So you're essentially integrating a signed distance function and a Parson window type density estimation into one representation, which is complex, which has a very close resonance to what we saw in Roberto's talk, where he went from real representations to complex representations. So basically, this is a good takeaway that this is the extra information that you have in the signed distance function. Okay, so take a look at some examples of the. I'm now just plotting the phase of the wave function, where what we have done is we've taken these shapes that were given to us by a colleague and used the normals. So the only additional information to the shape points are these normal information. And what you're seeing is I'm plotting the 0 level sets of the phase. And don't worry about the fact that the phase of the wave function are going to be wrapped. The wrapping has no impact here, because wrapped or not wrapped, they can still plot the 0 level sets. So this is what it looks like. And in addition to this, you have the magnitude information that is given to you by the magnitude squared, which is the density function of the shape. Okay, so what you can now do with this is that you can minimize a closed form distance between these implicit curves and surfaces. So this is what we did. We set up a regularized distance between wave functions in 2D and in 3D. So we went from an oriented point set template, which you see on the left here, to a target, which is just unorganized. And what this allows us to do is it allows us to endow the target with normals, and also endows us to take this particular template and take the wave function distance and have it map onto the target. So the math is very straightforward. All it is you compute the L2 norm squared of the source and the modified target wave functions. Phi composed with T is just the mapping that we have on the target. And I think that what would be very interesting would be to take these kinds of L2 distances that we get and try to rewrite them in the form of Hamiltonians. Because then what that would mean is you might be able to, and of course this is a long shot, you might be able to take this and eventually map it onto a quantum computer. But that's something that we can leave for the future. And obviously the work that Michael alluded to toward deformable matching with shapes, right, gives us tremendous room for encouragement that we could imagine this kind of computation being carried out in a quantum computer, where please note that the wave function would be implicit. We have no access to the wave function. Instead, you may end up with some kind of tensor representation for the underlying shapes where the wave function would be implicit. Of course, here there is a regularization of the mapping, which is important, and the regularization is just a spline that's being regularized in this manner. Okay, so I am not going to spend too much time on this. This is you can see it's a bit of a con in a multiple curves data set, we were able to show that we get pretty good results. But of course, the reason is that we have this extra information in the form of surface normals, which you don't have in the case of point cloud matching. However, it would be very interesting to conduct a careful study where you have a Parson window density estimator, where you have points and normals, versus a wave function estimator where you have an implicit representation with points and normals in the way we have set it up, and compare them to apples would be very interesting. Okay, I think that I'm running out of time. So in the interest of time, what I will do is just skip over this. Basically, we took this further to Mumford-Shaw, and we were able to show that that a Mumford-Shaw regularization simplified tremendously when we introduced a complex wave representation. And unfortunately, when we explained this with a lot of interest to computer vision researchers, we got absolutely no feedback from anyone at all, with perhaps the exception of Daniel Kremers. So this is something that could be interesting for the future. I'm going to skip that. I'm just going to do a quick shout out to this kind of work, which is where instead of a density function, you can represent numbers as tensors, and then start even going from a humble histogram to a density matrix representation. And for more along this line, where instead of representing a single random variable, you have a set of random variables in the form of a tensor representation, and a density function would become a density matrix representation. Take a look at Tide and A. Bradley's thesis, which is, I think, fantastic in this space. Okay, so to conclude, I think we have shown that QM approaches are clearly viable, both from what Michael told you earlier and in this talk. And there's clearly a very close link between sign distance functions, Hamilton-Jacobi theory, and wave function representations. It remains to be seen, of course, whether these wave function representations can be taken further into a quantum computing world where the wave function would be implicit. Clearly, we have thoughts for the future based on our own experiences in doing this kind of work. So I'll just leave you with some thoughts, which I think had not been talked about earlier. And essentially, the one point that I think has not come up, which is that and Tolga alluded to this in the beginning, if you can think of this as sort of like we are bootstrapping a new world into being at this point in time, given the fact that quantum computing has arrived, there's certainly something that I think has been missed, which is the whole notion of interactive computer vision, which was very popular in the early 90s. So imagine in a distant future, you have tensor representations up the wazoo with subsystems. You can imagine that a world of annotation inside a quantum computer where you would have implicit wave function representations interacting with human annotators inside a QC. I don't think this would be too far off 40 years from now. And obviously, you would have a fight between collapsed and non-collapsed models of wave functions, because the role of the annotators in the system would be very interesting. So I leave that as something that I think Roberto, came close to this with his talk about Bayesian, a Bayesian way of looking at QC. But I want to take that further into positing that interactive computer vision could be a very useful place for QC to set ourselves apart from the classical world. That's it. Thank you so much.
Right. Thank you very much for this exciting talk. We have time for a few questions. I think we have one question over here. Yes, please.
Michael Felsberg from Linköping in Sweden. Thank you very much for an interesting presentation. I would have a question about the FFT-based solutions. They imply a periodic boundary condition, and I wonder to which extent this leads to artifacts in your distance functions.
So that's an excellent question. Just keep in mind that the distance functions only make sense when you compute them on a bounded domain. So what you can do is you can set up the periodic boundary conditions on that bounded domain at the end of the bounded domain. And so then it just repeats beyond that. So that becomes a non-issue. But that's not really the problem. It's a very astute question, but the real problem is not in the. There are two problems, right? The first problem is setting up the initial state itself. That's what Stephen Jordan pointed out. But the second problem, at least from a computing perspective, is the negative logarithm. So in fact, it may turn out that we may be better off working with exponentiated distance transforms, where the taking of the logarithm and going to a distance function itself might be somewhat artificial. Why would you want to work with a distance function? Because it's a logarithm of a wave function. Instead, if you work with the wave function itself, you might be able to set that up in a Hamiltonian and then do more work implicitly. So that's sort of what I would urge. The focus on the setting up problem, as Stephen Jordan pointed to, and then also the move away from the logarithm and instead have it as an implicit wave function with a Hamiltonian in a implicit setup.
So is my understanding correct that you move the problem, so to say, to the inside of the domain so that the boundary is far away from the domain of interest?
Sorry, yeah. Going back to your original question, in a distance function computation is always on a bounded domain. So if the Fourier domain coincides with the bounded domain, there's no problem. The repetition is only beyond that. The boundary conditions are on that domain itself. So unless if you move the bounded domain to inside the domain for the Fourier, then you'll have a problem.
Okay, thank you.
All right, unless there are no other small questions, let's thank Anand once again.